net equals ma. Hi, and welcome to the freaking fantastic physics funhouse. I'm Professor Karjan Bergenheimer. Now today you're going to learn about the many and marvelous uses for physics. You have to understand, though, that physics isn't all numbers and equations meant to confuse and confound you. Okay, it is, but today will be different. Today you will learn about physics. So I was just hanging out at my house yesterday. My mom comes up and she's just like, "Yo, tell that cat F net equals ma."
Yeah, I know what you mean.
Whoa, what the
Heck.
hell is that person doing? Oh my god, is that a cat?
Oh my god, I hate drowsy cats!
Dude, that was insane.
No. Let's look at the physics behind this.
Alright.
When the crazy man threw the cat off the roof, he gave an initial velocity of VO, and at a height h, and assuming the air resistance on the cat was negligible, we can assume that the cat will land a distance x away from its original position. To find x, we first need to split up the variables into horizontal and vertical. Here we can see that in the x direction, or the horizontal direction, the cat's initial velocity was VO, it landed a distance x, which we are looking for, it had no acceleration, and we do not yet know the time. In the y direction, or the vertical direction, the cat's initial velocity was 0, it started at a height h, the acceleration was approximately 10, which is gravity, and again we do not yet know the time. Now to solve for x, we will use the kinematics equation x equals VAOT plus 1/2 AT squared. First we'll use the vertical components to find our time. We plug in h for x, 0 for VO, and 10 for acceleration. Notice that plugging in 0 for VO will make the left term cancel, leaving us with only the right term to simplify. Solving for t, we discover that time equals the square root of h over 5. Now we will use the horizontal components to solve for x. We plug in x for x, VO for VO, and 0 for acceleration. Notice here that plugging in 0 for acceleration causes the right term to cancel, leaving us with only the left term. Now plugging in t from our vertical component, we find that the distance the cat travels equals VO times the square root of h over 5.
Wait, using those physics, they must have landed.
Exactly 14 feet away.
Ah, sick. Physics is awesome.
Yeah.
Oh, I'm so tired.
So yeah, based on the superimposed string theory, F net equals ma.
I see now.
Yeah. Oh, can you help me bring the quantum spectrophotometer over to Mr. Karjan Bergenheimer's room?
I sure can, Alan. You just hang out with your girly woman arms.
Alright, dude.
Pansy. Flower. Alright.
Yeah, let me get it, dude.
Are you sure?
But yeah, based on the quantum field theory, I was pretty surprised.
Now watch out for Jake! Oh my god. Are you okay? Are you alright, man?
Dude, I can't walk.
You can't walk. Here, I'll carry you. I'll carry you.
Hold on a second. Let's look at the physics behind this.
When Alan tripped over Jake, he pushed the box onto the table, allowing a force diagram to be composed. Here we see a free body diagram, which shows all the forces on an object at a given time. Here we see that the force of gravity, labeled Fg, points straight down. This force creates an opposite force of the table on the box, pointed straight up, called the normal force, labeled Fn. There is also the force that Alan is exerting on the box, that points straight right, labeled Fa. And since there is friction between the box and the table, there exists a frictional force, which points straight left, labeled Ff. To find the force that Alan exerted on the box, we first must understand two of Isaac Newton's laws of physics. The first being net force equals mass times acceleration, or F net equals ma. And the second being that every force has an opposite and equal force. Using F net equals ma, we can say that the gravitational force, Fg, equals mass times the acceleration due to gravity, labeled g. Since forces are opposite and equal, we can state that Fg equals the normal force, and therefore the normal force must equal mg as well. We are given that the normal force equals the coefficient of friction, labeled mu in Greek or the letter u, times the frictional force. Since forces are opposite and equal, the frictional force must equal the force of Alan. Substituting the force of Ln for the frictional force and mg for the normal force, we find that mg equals mu times the force of Ln. Solving for Ln, we get that Fa equals mg over mu.
Suck it up, you pansy! You make me some flowers now! One! Whoa! I got loose, Dad. You're huge!
To begin, when Ln lifted the weight, he exerted what we call work on the bar. We define work as the force on something times the distance it moved times the cosine of the angle between the force and distance vectors. In this case, Ln exerted a force F over a distance d, and since the force vector and distance vector point in the same direction, the angle is 0. The cosine of 0 is 1, so we can ignore that term, and we are left with W equals F times d. At the moment that Ln dropped the bar, all the energy in the bar was in the form of potential energy, which is notated in physics as an uppercase U. Potential energy is equal to the object's mass times the acceleration due to gravity times the height of the object. Plugging in, we find that at the very beginning of the descent of the bar, the potential energy is equal to its mass times g times the height of the bar h. Here we see that just before the bar hits Ln's chest, all its energy is in the form of kinetic energy, which is notated in physics as an uppercase K. Kinetic energy is equal to 1/2 the object's mass times the speed of the object squared. Plugging in, we can see that the kinetic energy of the bar is 1/2 mv squared. One rule of physics is that energy is always conserved. Here we show that the total mechanical energy equals the potential energy plus the kinetic energy. When the bar was at the top, all of its energy was in the form of potential, and when it was at the bottom, all of its energy was in the form of kinetic. Using the law of conservation, we can conclude that the potential energy at the top must equal the kinetic energy at the bottom. Now we can set these two values we previously found equal to one another. Notice that in this case the mass will cancel out, and when solving for the velocity, we find that v equals the square root of 2gh.
My girlfriend yesterday, freaking F net equals MA. Like, who knew?
I know.
Alright, watch this shot.
Wow. Way to suck jewels.
Why don't you just take your shot?
Shut up, Carnation. 8-ball, corner pocket.
That's game.
That's right. What are you gonna do? What are you gonna do?
Hey, let's look at the physics behind this.
When Kevin originally hit the white ball, he gave the ball momentum, which is notated in physics with an uppercase P. We find that the momentum equals an object's mass times its velocity. The total momentum before the two balls collide is the sum of the momentum of both balls. The white ball has a mass m and a velocity v. The black ball is more dense and has a mass of 2m, but since it is not moving, its velocity is 0. Plugging in, we see that since the black ball has no velocity, it has no momentum, making our total momentum before the collision equal to m times v. Here we see that at the point of collision, all the momentum of the white ball is transferred into the black ball. After the collision, we find that the white ball has stopped and has no velocity, and the black ball is moving with an unknown velocity. Now to solve for the total momentum after the collision, we again take the sum of the momentum of both balls. The mass of the white ball is m and its velocity is 0. The mass of the black ball is 2m and its velocity we will label va. Since the white ball has no velocity, again we see that it has no momentum, making the total momentum after the collision equal to 2mva. Another law of physics is that momentum is always conserved. Therefore, we can assume that the momentum before the collision will equal the momentum after the collision. Plugging in the two values we previously found, we can now solve for va. Notice here that the mass cancels out, making va equal to v over 2.
We really should be doing this, you know. This is illegal.
Shut up. It's not like the cops are gonna show up.
Yeah, I guess.
Freeze! Get back here!
Run! Over!
Get over here! Get over here! Alright!
Ah, it's the popo!
Get over here! Alright! Alright, you're under arrest! Get over here! Alright! Get over here!
Ah!
In this case, the collision is inelastic, meaning that the two masses that collide stick together instead of separating like the billiards did previously. Here we can see that before the collision, Kevin had a mass of uppercase m and a velocity of v1. The random jogger had a mass of lowercase m and a velocity of v2. To find the total momentum before the collision, we take the sum of both Kevin and the jogger's momentum. Plugging in, we find that the total momentum before the collision equals uppercase m times v1 plus lowercase m times v2. Here we see that when Kevin and Ellen collide, their momentum is combined since they stick together. Remember, this is what we call an inelastic collision. After the collision, we see that since Kevin and Ellen combined, we also combined their masses, and they share an unknown final velocity labeled vf. We can solve for the total momentum after the collision by plugging in the sum of the mass of Ellen and Kevin for m, and vf for v, giving us the total momentum of the quantity uppercase m plus lowercase m times vf. Remember that momentum is conserved, and we can assume that the momentum before the collision equals the momentum after the collision. Plugging in the two values we previously found, we can solve for vf. We find that vf equals uppercase m times v1 plus lowercase m times v2, all over the sum of uppercase m plus lowercase m.
Yeah, you alright? Okay, you know what would make that better?
What?
Some Kool-Aid.
Yeah. Dude, I got no one to mix it though. Hey, Kev, wanna mix these for us?
Here, Kevin, hold that for a second.
Alright.
Alright, we're just gonna
Yeah, real quick.
Whoa. Alright, you gotta put out your arms.
Yeah, you gotta put it out.
Oh,
Wait, bring it back in.
yeah.
Oh, I'm getting so dizzy.
Oh,
Dude, you don't look so good. You don't look so good.
oh my god.
You alright? Mom, Kev threw up.
It's everywhere.
When we began to spin Kevin, he developed what we call angular momentum, which is notated in physics as an uppercase L. Angular momentum is calculated as the moment of inertia of the object spinning, notated as an uppercase I, times the angular velocity, notated as a lowercase omega in Greek or an uppercase W in this instance. If we consider Kevin to be a solid disk, he will have a given moment of inertia of 1/2 mr squared, where m is his mass and r is the radius from the center of the circle his body makes to the outside. Using this, we can find that the total angular momentum before he extends his arms is 1/2 mr squared times W. Here we can see that when Kevin extended his arms, he increased his moment of inertia by creating point masses, assuming his arms are negligible. The moment of inertia of the two bottles are both mr squared, where lowercase m is the mass of the bottles and r is the distance from the center of the bottle to the center of Kevin. This made his new moment of inertia 1/2 mr squared plus lowercase mr squared plus lowercase mr squared. In combining these, we find that the moment of inertia simplifies to 1/2 mr squared plus 2 lowercase mr squared. Substituting this in, we find that the angular momentum after Kevin extends his arms is equal to the quantity 1/2 mr squared plus 2 lowercase mr squared times WA. Like linear momentum, angular momentum is also conserved. Therefore, we can conclude that the angular momentum before Kevin extends his arms is equal to the angular momentum after Kevin extends his arms. Plugging in the two values we found previously, we can solve for WA. When fully solved, WA is equal to 1/2 mr squared times W, all over the quantity 1/2 mr squared plus 2 lowercase mr squared. This shows that the angular velocity after is less than the angular velocity before, which if you remember from the video explains why Kevin slowed down when he extended his arms, and then sped up when he brought them back in.
Just gonna hit a few balls over here.
When Kevin swung the golf club, he created a simple pendulum, assuming the rod of the club was negligible. The motion he created is known as simple harmonic motion, abbreviated as SHM. Under this motion, we can say that the period of motion, notated as an uppercase T, is equal to 2 pi times the square root of the length of the pendulum, notated as uppercase L, divided by the acceleration due to gravity. Another important concept to note is that at the endpoints of the swing, the potential energy is at its greatest, and therefore the club is at its maximum height. We must also note that the acceleration always points inward, and that the velocity is always perpendicular to the acceleration. In contrast, at the exact middle of the swing called the equilibrium point, the kinetic energy is greatest, and therefore the velocity is at a maximum. Again note that the acceleration always points inward, and that the velocity is always perpendicular to the acceleration.
push me, and then just touch me, till I can get my satisfaction.
Push me, and then just touch me, till I can get my satisfaction. 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 Satisfaction.
Action.
Oh, I'm so tired.
So yeah, based on the quantum spectrum photometer fields, pretty much every one I
I see.
Oh, can you help me bring the quantum spectrum photometer over to Mr. Kargenberger in Neighbors room?
Of course I can, Alan. Just don't worry about it. You and your woman arms can stay over there and hang out.
All right,
I'll
man.
carry this.
Dude, I got it. Yeah, I was surprised about the quantum field fluctuation.
Jake, what?
Screw it
Alright.
up. So yeah, I was talking to my girlfriend yesterday. Friggin' F not equals MA. Dude. Alright, watch the shot. Damn it.
Well, Alan, why don't you suck some more jewels?
Hey, why don't you take your shot?
Shut up, Carnation. Alright.
Damn it.
Dad! So yeah, I was talking to my girlfriend yesterday. Freaking F not equals MA.
Oh,
Like, who knew? But, alright, watch the shot, dude. God. Yeah, I was talking to my girlfriend yesterday. Freaking F not equals MA. Like, who knew?
yeah.
Watch the shot, dude.
Alright.
Damn.
Wow. Why don't you suck some more jewels?
Hey, why don't you take your shot?
Oh, shut up, Carnation. Alright, here we go. 8-ball corner pocket. Damn it!
You like that, Jake?
Dude, we really shouldn't be doing this though. This is illegal, you know.
Oh, shut up. The cops aren't gonna show up or anything.
Yeah, guys. How are you smart? Who's smart? Cut.
Oh my god! Oh my god! This is what happens.
Alright, Kev, we'll go clean you up.
Alright.
That was a good fall, though.
Oh my god. I love physics. It's my favorite.
Physics is so much fun.
Take off your shoes.
You take off your shoes. Ooh, now this is getting to be a fun video.
Gross.
Kevin fell on his butt.
There, Dave, hold the camera.
Oh, I got you.
I gotta clean up, Kev. It's rolling. It's
Make it
rolling.
hot. Oh, hey, Kevin. Nice mustache. Kevin and Alan, 1 cup. Oh, what you getting, Kev or Alan?
I thought there were band-aids in here. This time.
Nah, just put some rubbing alcohol on that thing. Put some salt in there, and
I'll
you're
just rub
good.
some dirt on it. I'll be fine.
Oh, Kevy Poo hurt his leg.
Ow.
Yeah.
Do we have a suit?
Jesus. Operation. Is it water on the knee? Sure. Hey, Kevin. This looks interesting. So, Kevin,
So, Dave.
while I got you here,
Yeah, alright.
let's get a little interview, huh?
Yeah.
So, How do you think Brad Pitt would have done that? I think he would have done it perfect.
I definitely think Brad Pitt would have been 10 times hotter. Definitely
doubt it.
Definitely
I doubt
better
it.
looking than me.
I doubt it.
Yeah. That's alright, Dave.
Oh, God.